Hey, Calculus 3 students. Here we are as part of our activity replacing class for Friday, April 28th. We're going to do some examples here via video. Hopefully it will be moderately entertaining watching me try to remember how to do this. So I'll move myself down here and then we'll see what we could do as far as getting this example done. So for our first example, this is example 1 in course notes section 2.1, so you could follow along there or try to do it yourself first. This is to compute the length of the asteroid. Okay, we talked about the asteroid a little bit in class already. If you remember, the asteroid has, let's see if this is, oh, there it goes. It has rectangular equation. Yeah, this is going to be interesting. X to the 2/3 plus y to the 2/3 equals 1. And so you can see right away from that if you replace x with negative x or y with negative y, it doesn't change anything. And that tells us that this curve is going to be symmetric about both the x-axis and the y-axis. For that reason, when we go ahead and compute its length, we can compute the length of just 1/4 of it. Now, we haven't graphed the asteroid in class yet, but when we do, you're going to see that it roughly has this kind of a look to it. Okay, and that's supposed to be symmetric. This piece didn't come out too smooth. Okay, it's got that kind of a look to it, and so what we could do is we can concentrate on just one. Let's see if this, how does this work? Yes. Let's see if I'm able to do this successfully. Yeah, we can concentrate on just this portion of it right here and find the length of that. And then our overall length for the asteroid is going to be 4 times the length of that piece, which is going to be the integral from 0 to pi over 2 of our usual formula for arc length, which will be dx over dt squared plus dy over dt squared dt. Okay, so we could do that. And the reason why we not only want to do that for convenience, but we kind of have to do it, is because if you look at these cusps that the asteroid has, those are going to be points where it's not smooth. And arc length formula really works for smooth curves. So we're going to avoid those bad points by just focusing on this 1/4 of the curve. They're still on the endpoints for us, but that's okay. It's not too bad if they're on the endpoints. All right, so let's see if this can advance. Yes, there it is. All right, so now we're going to get into our computation for the asteroid, the length of it. Well, for that we need the derivatives of our parametric equations. And so we need dx over dt, and that's going to be, by the chain rule, 3 cosine squared t, and then sine t, but of course, since we're differentiating, we also pick up a minus sign on that. And then dy over dt, that's going to be 3 sine squared t times cosine t. Looks like it gets a little complicated, but and it will seem that way at first. It often does in these, but for the ones that we could actually do, they typically have some really nice simplifying down that happens. Okay, so now our length, we know we're going to do just the part from 0 to pi over 2 and multiply that by 4. And so we have the square root here of dx over dt squared. And so let's go ahead and take our, well, let's do this. Let's do -3 cosine squared t sine t. Okay, we need to square that. Okay, and then we got to add in here the square of dy over dt. So that'll be 3 sine squared t cosine t We're going to square that. Then we take the square root, we multiply by dt, and then we just got to integrate. So right now this looks like a complicated integral, but let's rewrite it and see what happens. So first thing I'm going to do is actually square the two derivatives here. Okay, so we'll get 9 cosine to the 4th t sine squared t. And then for the other one, 9 sine to the 4th t cosine squared t. Got to make this square root go further over. Okay, and now we start to look at some stuff that we can simplify and get out of here. So we've got 9 common in both terms there. We can factor that out, and then we can actually take the square root of that right away as well. And so we'll have a factor of 3 out front here. And then we've got our square root. Okay, and within that, if you notice, there are common factors of cosine squared and sine squared in the terms there. So let's do cosine squared, sine squared. Whoops, got to have a t in there as well. Okay, and then what's left after we factor those out is, well, cosine squared t in the first term and sine squared t in the second term. Well, wouldn't you know, like we said, things start to simplify down a little bit here. Hopefully you notice cosine squared t plus sine squared t, that's just going to be 1. And then under our square root, we're going to have left cosine squared t, sine squared t. We got a square root on those. We could just take the square root. Now you may say, what about plus minus? Do we have to worry about those being negative? And the answer is no. If you look at our interval again, we're over the interval from 0 to pi over 2. And so we don't have to worry about anything being negative. Their square roots are just going to be themselves. Go ahead and pull that 3 all the way out. And combine it with the 4 to get 12. And so what's left in our integrand is just cosine t sine t dt. And that's an integral that you should be able to do in your sleep just about. It's now a very manageable and doable integral. So what we would probably do there is a substitution. And you take your pick here. It's going to work either way, but just to avoid a minus sign, we'll let u be sine t, so that du then is cosine t dt. And if we want to go ahead and change our limits of integration, that's certainly an option for us here. If we do that, we would say that when t is equal to 0, that correlates to u being 0 as well. And when when t equals pi over 2, u equals 1, because sine of pi over 2 is 1. So converting everything to u, we end up here with the integral from 0 to 1 now of u to u. And that's really easy, right? So now we know anti-differentiating, we get u squared over 2. And evaluating at 0 and 1, that just gives us 1 over 2 minus 0. Okay, and then remember we have that factor of 12 out there. So multiplying, we end up with a final value of 6. All right, so keep in mind we had already had that multiple of 4 in there. So this entire length all the way around that asteroid is 6. It's interesting when you think about it. It's kind of got a little bit of a circular, like a flipped circular feel to it. But a circle of radius 1, that would be 2 pi around. That's about 6.28. So this is a little bit shorter around, a shorter length than the circumference of a circle would be if it had that same sort of radius that the asteroid does. Okay, so that's example 1, first example of computing arc length, and we got 6, amazingly enough. Okay, I think that's all I was going to say about this one, and we'll see you in example 2.